Hello, all my advanced math fans. Here's what we have going on for today. I wanted to talk a little bit about statistics still, but I want to talk about inferential statistics, it's called. So, we have stats where we can survey everybody. However, in a lot of circumstances, that's just impossible. If we wanted to, say, survey the population of the United States, it's impossible to send out a survey to over 300 million people and get responses back from all of them. So what you do instead in these situations is you do what's called sampling. And so a couple words that go along with this. The population is the entire group that you're trying to study. So it could be like the entire population of the United States. Could be just a certain age group in the population of the United States. Could be just a certain age group in Ohio. It just depends on what you're trying to survey. And then a sample is, and this is a very important word in this, a sample is a representative portion of the population. And so instead of sampling or instead of surveying the entire population because it's just not feasible to do in a lot of circumstances, we take a representative sample of that population. Now it has to be representative. This is easy to mess up and get a biased survey, it's called. So let me give you some examples of some biased surveys. If you wanted to find the average height of men in the United States, however, you went around and asked NBA players, you're going to get a very biased answer because the average height in the NBA is not the average height of a normal man in the United States. And so that's a very big example of a hugely biased survey, but things like that, and they can happen more easily than that in certain situations. And so that's an example of a survey that's not representative for a population. So we have to make sure if we're doing a sampling that it's representative of the population and that it's not biased to a certain outcome. So when we do this, anytime we're doing a sample and not doing the entire population, there is error. If you're not asking everybody, you don't get perfect results. It's just not possible unless you ask everybody in that population. So what we're going to compute today is a thing called the standard error of the mean. So this is basically, here's our symbol for this. It's like the standard deviation symbol with a little mean subscript, a little x bar subscript. And the way we compute this thing is we take the standard deviation of our sample and divide it by the square root of n. Now remember, n stood for however many people or however many data entries there were. So if we ask 50 people something, n is 50. And so that's how we find the standard error of the mean. Now the reason we use this symbol is because what this tells us is how far on average the sample means should be off. Or in other words, it's basically like the standard deviation of the sample means. And so that's what this is all about. It's telling us how far off the mean is as a general rule. Now, this is something, I could give you a whole table of these, but really the only levels of confidence that are used a lot in statistical analysis are 99% confident, 95% confident, or 90% confident. And so you could say a 1% margin of error, 5% margin of error, 10% margin of error to put those in different terms. I put the numbers that go along with these because what these numbers represent is how many standard deviations we want to go from the sample mean up and down to get an interval with this amount or this percent of confidence. And so if I wanted a 99% confidence interval, I'd have to go 2.58 of the standard error of the mean up and down from the mean in order to get this interval. We're going to do an example of this. I think I'll clear this up in a minute, but you might just want to jot these numbers down. This is an important little thing here. And really you could do some work on our z-tables and figure out why these numbers are what they are, because it really is just based on that standard normal curve still. But I figured I would just give you these because these are just the common ones that are used. So let's look at an example and see if we can do this. So on this one, we're going to say a sample of 50 college students in Ohio are asked how many hours a week they work. So if they're asked how many hours a week they work, the mean is 16 hours and the standard deviation is 2 hours. So let's see if first off we can find the standard error of the mean. Now, this number has nothing to do with the standard error. The standard error, remember, is the standard deviation over the square root of n. So do you notice we sampled 50 college students? In other words, n is 50. The standard deviation is 2, so to find the standard error of the mean, we would want to do 2 over the square root of 50. Now, standard error often comes out to a fairly small number, and that's good. You don't want this error to be a huge number. And this comes out to about 0.283. So about 0.283 is our standard error of the mean. And so if I want to know what is the interval that we are 95% confident the population mean falls in, well, that's where this number is going to come into play. And so basically we want an interval, we want a low point and a high point around this mean that we found. And so here's basically what we're going to do. We're going to do 16 and we're going to go up and down. So I'm going to say plus and minus. Now since we're doing 95% confident, I'm going to use 1.96. So we're going to go 16 plus and minus 1.96 of the standard error of the mean. The most common mistake on these problems is using the standard deviation here instead of the standard error of the mean. If you use the standard deviation, you're going to get a huge interval. What you're getting basically is the interval that contains 95% of the data. That's not what we want. We want a smaller interval around our sample mean that we're 95% sure that the mean for the entire population, for everyone, falls in. And so if I do this, well, here, I'm just going to go ahead and figure out all this stuff. So remember, like PEMDAS, multiply these together first and then do plus and minus that from this. And that gives us, on the low end, 15.45 approximately. On the high end, it gives us 16.55. And so there's our interval. Now, I really wanted to say this because this is kind of an important thing if you're doing a statistical study, to be able to state what this means clearly. So in this particular survey, do you notice who we were asking were college students in Ohio? We didn't ask all college students in Ohio, we asked 50 of them. But our population, the whole group we're trying to generalize our results to, would be all college students in Ohio. So here's how you could say this. We are 95% sure that the mean hours worked for all college students in Ohio is between 15.45 and 16.55. Now, the reason you can't say the mean hours worked for college students in Ohio is 16 hours is because we did not ask all college students in Ohio. We only asked 50. So that creates this margin of error. That's what this interval is for, is saying we can't be 100% sure, but we can be 95% sure that the population mean, or the mean of all college students in Ohio, hours worked is between 15.45 and 16.55. So that's the statement you can make with this information. All right, so there's how we do some inferential statistics. There's a lot more to this topic, but I wanted to at least brush the surface and get an idea of what we find here and what this stuff means. And so these are important numbers, remember, because these are the margins of error that are used most often in statistical studies. Remember how to find standard error of the mean, and then remember when you go to find a confidence interval, it's the sample mean you ended up with plus and minus whatever percentage you're using. Use that number for your, basically like your z-score almost, and then multiply that by the standard error, go that far up and down from the mean. There's your interval where you're a certain percent confidence that the population mean lies.